Welcome to my classroom. We know that mass transfer operations are employed for separation of the components of a solution. The solution so separated may be a solid, a gas, or a liquid. In majority of these operations, the transfer of mass occurs between two insoluble phases which are in direct contact. Okay, the common mass transfer operations falling under these categories are distillation, gas absorption, liquid-liquid extraction, drying, leaching, adsorption, humidification and dehumidification, crystallization, ion exchange, etc. In mass transfer, the material is transferred on a molecular scale, and this transfer is quite different from the bulk transport of material from one location to other location, just like in the case of pumps and blowers. Okay, so there some external forces traveling or facilitating the pressure movement. Okay, and this bulk transport of mass is distinct from the mass transfer, which involves the relative movement of the components due to a concentration difference. Say for example, what we are inhaling oxygen. Okay, the inhalation of oxygen air by the lungs is bulk transport, whereas the transport of oxygen into the blood is diffusion. Okay, so that difference we should know. What is bulk transport, what is mass transfer. Okay, so that way we should know all the difference between what is bulk transport of mass and what is mass transfer. Okay, so for a mass transfer to occur, we need presence of two regions at a different chemical compositions. Okay, there should be a concentration difference between two regions, so that relatively there is movement of species taking place from one place to another place. Okay, this may even take place within a fluid mixture, or it may take place across a phase. Polymers. So for example, thin, dense and non-porous polymer membranes have been widely used to separate gases and liquid mixtures in the industries. And the mechanism of diffusion is strongly dependent on the what type of polymer is being used. So we may be using it can be a crystalline, or it can be amorphous. Okay, so or it can be glassy or rubbery type polymer can be used, right? And commercially, crystalline polymers are about 20% amorphous, and it is mainly through the amorphous region that diffusion is taking place. And the transport of gaseous species through a polymer membrane is usually characterized by the solution diffusion mechanism. Okay, we will discuss about polymers, and we did even numerical. In the previous class, we solved a numerical on hydrogen diffusing through neoprene rubber. Okay, so that is actually coming under this category, diffusion through polymers. So if you look at the diffusion through polymers, so we will actually, what is that? You are having a solid. If you consider membrane, a membrane is there, you have a solute. Okay, so this has to diffuse through it, and there is a possibility that inside this polymer some amount will be retained, because depending upon the size, molecular weight, and what is the velocity, what is the concentration difference. In this side the concentration of the solute is Ca1, in this side the concentration is Ca2, and if the thickness is Z, so we are going to always, there will be pressure. Pressure is different, right? Concentration or pressure, whatever. If it is gaseous solute, you can say Pa1 and Pa2. Okay, so always if there is high pressure and this side there is a difference in pressure, so the partial pressure of solute in this side is high and in this side it is low. So obviously there will be diffusion from higher concentration to lower concentration to the solids, and it also depends upon how freely it can travel across the polymer, right? So actually polymer is like you have a chain of polymeric membrane. So actually what will happen, these membranes will be in depending upon the temperature, this chain will be continuously vibrating or something like that. Okay, so that the chains are in continuous motion, or it will be vibrating. So what happens is, from one place to another place, this solute molecule has to go through, means diffuse through it. Okay, so and there is a possibility that some will be retained in the solution, right? So it depends upon in any solid how much. Say for example, you have a sponge, how much water it can contain, rest of the water only will be allowed to go through it, right? So similar to that, if you have some thing, it depends upon the solubility in it also. Okay, so how much it in polymer we are talking about. In a polymeric membrane or any polymer, certain amount of solute can be retained by the solid. So beyond which it will be passing through it also. Okay, so then it will permit to go. Okay, for example, you are sitting in a wedding hall, you are capable of taking 5 rounds of drinks. Somebody taking drinks first time, you will take it. Second time, you will take it. Third time, you will take it. So only you are done, then only you will allow the person to pass through the next person or next thing, right? So that way, till we can whatever we can contain, that solute will be contained by the polymeric membrane or polymers. Okay, then only the rest will be allowed to diffuse through it. Okay, so again here we will be introducing like solubility coefficient. Okay, so then we will introduce what is permeability, and we have diffusivity, mass diffusivity. So these three are related. Okay, so if you look at any diffusion of solute through a certain polymeric solids, it is like similar to diffusion through a liquid. Okay, most of the cases it is similar to in a liquid how the solute will travel, so it may travel. Okay, other than that, at least for permanent gases, the diffusion is simple, easily, because the depending upon the size of the molecule, the solute A, if the molecule size is very small, it will easily diffuse through it. Okay, it's similar, it can be related to diffusion through liquids also. Okay, so obviously depend like Henry's law, we know the concentration is directly proportional to pressure. So we already seen that depending upon the pressure difference in the either side of the polymer, so we are going to have the diffusive flux. Okay, obviously and one more thing is that it will be happening just like an activated state, that I said, as the polymeric chains are in the state of constant thermal motion, and this molecule is like it is a jump of molecule from one gap to another gap. Even though some molecule is jumping, once I reach here, there should be a gap or a passage for this molecule to go there and move there, otherwise it will go back to its original position, right? So like that, this is how it happens. The polymeric chains are in the continuous thermal motion. The diffusing molecule will be trying to jump from one position to another over a potential barrier. That is like minimum potential barrier will be there. So once it is more than the barrier, then it will going to another place. Otherwise, it will return to its original state. Okay. So obviously, this size and hole available will depend upon how this thermal motion is there. Okay. And there is another type of solutes which may be plasticizing the polymer and then diffuse through that one. Okay, so if it is plasticized, then there will be continuously diffusion which will be higher. For example, if we have benzene or methylethyl ketone in a polymeric rubbers, so first what will do is first time they will even plasticize the polymer. Once it plasticizes the polymer, we are going to have higher diffusion rates. Okay, so in these cases, in general, in diffusion in polymers, it's going to be the effect of temperature will be there. So we can have a similar to in CRE, you will have Arrhenius type of reactions, right? You have Arrhenius type of reaction, dA equal to d naught into e power minus h d by RT. Okay, so you will have heat, it's like a barrier potential, that how much heat is required for the diffusion jump to occur, or temperature. D naught is reference diffusivity. So diffusivity of any solute at a given temperature is a function of its diffusivity at reference condition, and it varies as a function of temperature. Okay, so in general, for gases, permanent gases, in the sense it is like hydrogen, nitrogen, oxygens. So for this type of permanent gases, diffusion in polymer will be in the range of 10 power minus 10 meter square per second. Okay. So if this is the polymer, so this side high concentration is there, another side lower concentration is there. So the diffusion will be taking place from the higher concentration to lower concentration. It's similar to heat transfer through a slab, metal slab is there. In this side you have high temperature, this side lower temperature. Heat transfer will occur, and we assume it to be linear, right? Across the uniformly, it is varying across the given thickness of Z. Okay. So yesterday itself we seen this expression. So we define the solubility coefficient, which is also called as Henry's law constant. So the unit for the solubility coefficient is centimeter cube gas per centimeter cube of solid. It is how much centimeter cube of gas can be contained in a centimeter cube of solid per pressure per atmosphere. That means if this is the per centimeter mercury. This is a unit given here in the definition. We can convert always to SI units. So that means for at any temperature or at any pressure. So if I want SA at P2 centimeter Hg, I have to multiply by P2 and the unit will get cancelled, so that I'll have SA at a given pressure. That is the important thing we should do while solving the numerical also. So this it has divide is given defined with divided by pressure. So always we have to multiply by pressure to get the SA value, solubility coefficient at operating pressure. So for operating pressure, so this SA in given value should be multiplied by total pressure, means operating pressure. Okay, so that the CM we have to substitute it in centimeters of mercury, and the centimeter mercury will get cancelled. Then you have solubility coefficient of centimeter cube of gas contained per centimeter cube of solid. Okay, so this is solubility coefficient, and it is related to concentration as solubility coefficient into partial pressure gives us concentration. Okay, so this product is equal to this. So 22.414 is 1 kg mole of any gas will occupy this much volume. Recall what you have learnt in process calculation course. What is Avogadro number? How much per gram mole will occupy 22.4 liters of volume, or you can say 1 kg mole of any gas molecules or species will occupy a volume of 22.4 meter cube. Okay, so that way we using this relationship we can always get CA value. Okay, that CA can be obtained, and this permeability is defined as product of diffusivity into solubility coefficient. Okay, so permeability of any polymeric membrane can be determined is a function of diffusivity, you can see here. So that way this diffusivity is used to determine the permeability. Okay, so if you want to determine the mass flux or diffusive flux, so I gave you this expression yesterday, VA equal to dA into SA into dCA by dZ, or PA1 minus PA2 by Z. So PA is the partial pressure of diffusing solute, dA is the diffusivity. This we have to substitute in this given units, centimeter square per second. Partial pressure has to be substituted in centimeters mercury. This diffusive flux is given with this unit, centimeter cube of gas at STP by centimeter square per second, and finally we can convert to SI units. Okay, even convert all the expression in SI units also, then you can make use. Okay, so if you look at using this expression, how to get familiarized with permeability and solubility coefficient, you can go through this problem, because this type of applications is there. Polymeric membranes are used in various applications, including if you have hydrogen gas separation from a refinery waste gas, we will have a type of, there will be 1000 tubes in a single shell and tube heat exchanger type. Okay, so there will be 1000 tubes of 0.4 centimeters or mm thickness. So you will have, so if you see the cross section area, you will have so many tubes will be there, so through which you will passing through this waste gas, from which hydrogen will be diffusing through the tube. Okay, so that is an example for this diffusion through gas, diffusion through solids or polymers. So take down this problem. Calculate the rate of diffusion of CO2 through a membrane of vulcanized rubber 1 mm thickness at 25 degrees Celsius with the partial pressure is 1 centimeter mercury on one side and 0 on the other side. Even if it is not given, we are going to take like that. Calculate also the permeability of the membrane for CO2. Calculate the permeability. At 25 degrees Celsius, solubility coefficient is given. Diffusivity is given in meter square per second. Okay. So how to solve this? We have to substitute the values in this formula. But this formula is mentioned clearly in which unit you have to substitute. Change diffusivity is given in meter square per second. You convert to the centimeter square second. Partial pressure is given in atmosphere. Convert to centimeters of mercury. Then you can substitute here. Okay. Z also should be in centimeters. Okay. SA unit is given here. It is also given per atmosphere like that. You have to get multiply by the operating pressure to get the values. So first know the conversion factor. One standard atmosphere is, you know that atmosphere, one atmosphere is 760 mm mercury, we know, right? But here we have to substitute in centimeters. That means 76 centimeters mercury. Okay. So the solubility coefficient is given here this way, 0.9. So solubility coefficient SA at is given like 0.9 centimeter cube of gas STD STP per centimeter cube of solid per atmosphere. Okay. So result, first we have to convert to mercury, centimeters mercury. So conversion factor is 1 atmosphere is 76 centimeters mercury. We have the value. How much? Z is given as 1 mm thickness. We have to substitute in centimeters. PA1 is given. We are taking A as CO2. Okay. So PA1 is given as 1 centimeter mercury. PA2 is 0. That is 0 resistance.
Sir, you will get 0.0118.
0118.
18. Yes, sir.
Okay. Okay, so we have all the things to substitute in VA expression. What is the equation? How P can be determined? It is simple, that's all. DAB is given, right? So DAB is given 1.1 into 10 power minus 10 meter square per second. So 1 meter square is 10 power minus 4 centimeter square. So we have DAB value is 10 power minus 10 plus 4 is minus 6. Okay.
Diffusion rate of diffusion is 1.298 into 10 to the power minus 8 centimeter per second.
Okay. How much?
1.298 means 1.3 into 10 to the power minus 8 seconds centimeters per second. 298 10 to the power minus 8, sir.
Minus 6, no?
8 it came, sir. Centimeter per second.
Okay, that's the same. But we don't write in that way because we want to say it is how much gas per how much meter square per second. It's volumetric flow rate, not diffusive flux. We want to maintain this. Okay. Because this is centimeter cube of gas and this is centimeter square of cross section area of the solid. Okay. So keep this unit only. Did you check with this one? Are you getting same? Anybody getting 10 power minus 7?
Yes, sir. Sir,
So
I'm
for
getting
VA, I'm
1
getting as 1.29 into 10 raised to minus 7, and for P, I'm getting as 1.29 into 10 raised to minus 8.
Yeah. So
Yes,
1.29
sir.
into 10 power minus 7. Tell your names who are getting these values.
Sir, Anushka.
Preetha,
Okay, Vaishnavi, then
Sir, Anushka. Not right.
Preetha,
Balaji, Navya, okay,
Naveen, sir.
minus 7, na? Okay, name, check your thing, that's a Ganesha, what's the name? Okay, so the VA value you will get in this and write with this specified units, okay. Now this is, we have to get familiarized with this type of, when you talk about volume, we have to say centimeter cube but STP per centimeter square of cross section area of the solid per second, okay.
Sir, is DAB 10 to the power minus 7 or 10 to the power minus 6, sir?
DAB
Minus 7, sir.
minus 6.
Oh, okay, sir.
That's where you mean, no? Minus 10, it is given.
I put 10 to the power minus 7, sir.
Yeah, that's what it is. Take care. That's why show the substitution here, how we are converting meter square to centimeter square. Simple, no? 1 centimeter is 100 centimeter, 1 meter. So you will have 100 square. 10 power 4 centimeter is 1 meter square.
Okay, sir.
Okay, then determine P value. Substituting the values of DAB and SI in P, we get P equal to 1.1 into 10 power minus 6 centimeter square per second into 0.018 1184. Then the units of centimeter cube of gas per centimeter cube of solid into centimeters mercury. Okay, almost same value, no? Minus? Yeah.
It will be minus 8, sir.
Yeah, here 10 power minus 8. Okay. So write with the appropriate unit of P mentioned here. P P unit is centimeter cube gas into centimeter square second into centimeter mercury per centimeter. This adjustment only. Centimeter is here, centimeter here. You are what is the earlier unit? SEI unit is centimeter cube gas per centimeter cube centimeter into centimeter mercury. You are multiplying by centimeter square per second. Second is here, centimeter square is there. That adjustment is done here. Okay. Look at diffusion through crystalline solids. It has significance in metallurgy industries. Okay, because that is where we are talking about diffusion within the solids, how the atoms are moving from one place to another place. If you look at physical metallurgy, or if you want to study about corrosion, so corrosion studies, and if you look at mild steel, hardening is done. What physical changes is taking place from alpha phase to beta phase, how the metal gets converted from one state to another state, so that it becomes more harder, or it shows more resistance to corrosion. If we compare mild steel with stainless steel, the one which makes difference between them is chromium. Chromium is responsible for making the stainless steel stainless. Okay, the composition, the percentage of it varies from 10% to 30% depending upon the level, that is the grade of stainless steel, and in general it varies from 15 to 18% is normal one. Okay, that is available commercially. And actually this chromium oxide will be formed on the surface of the stainless steel when chromium is reacting with oxygen available from the atmosphere. That way that layer formed, chromium oxide layer formed over the stainless steel, will act as a barrier, thereby preventing the material from getting corroded. Okay. Some of the most recognizable items that is made with stainless steel are kitchen appliances, food processing equipment, medical and dental tools, and even the school bus that we used to board in the early morning is made up of colored paint. That yellow color paint that we see every day is chrome yellow for the chromium pigment, which is adapted for most of the school buses. Okay, even in our country also. Okay, that is because the black letter that is written on this chrome colored paint will be visible to easily of diffusion in solids. There are so many metallurgical operations like carburization is there, hardening is there. So what they do is they add carbon to carbon steels, addition of carbon to carbon steels at different temperatures. It is done at a high temperature like 850 to 950, or even in montacitic carbon hardening is done. Okay, so this all is done to increase its strength, resistance. Okay, so for example fatigue resistance or wear resistance. To improve that, these operations are being carried out at high temperatures. So at these locations we can observe diffusion is taking place. For example, if gears are there, okay, so we have the saw blades which can cut through hardened materials also. All these materials at the surface, these are the carbon is being added. Okay, so that they are called case hardening or surface hardening, where they harden the surface of the material. Okay, what we do is we are diffusing the carbon metal. We diffuse some of the elements onto the surface, which forms a thin layer. It looks like it even sometimes react to make a alloy. Okay, it will serve as a coating. So instead of having a paint coating with the metal itself, we have this thing. So that way, it diffuses from the internal surface comes to the surface and forms a thin layer. Okay, so that way only these carbon atoms are diffusing through the iron lattice atoms at the surface. So this is actually one of the example for diffusion in solids. Okay, so even if you look at the disk, compact disk, nowadays we are not using, but still this compact disk, if you look at it, this is a microstructure. There will be a thin layer of cobalt, platinum, chromium, all that. So a film is formed after annealing. So in this also, this chromium diffuses from the grains to the grain boundaries, after the annealing process, it helps to improve the magnetic properties of the hard disk which we are using. Okay, so here also this diffusion, where what do you see is this metal, or in earlier case we have seen carbon is diffusing, here we are seeing chromium is diffusing. Okay, and also in case of hot dip galvanizing. Okay, so this also used, this kind of materials are used for rust resistance, where we want to have rust resistance, so these galvanized beams are being used. Okay, so in all these cases we have one or another small material like carbon or chromium or zinc. Okay, so they diffuse through and form a layer. Even if you look at thermal barrier coatings like this, we have a ceramic top coat. So this is to avoid, means when you want to have this type of ceramic coating is to have provide some resistance to heat being carried away. Okay, so that way these coatings are being used. And if you look at this thing, even the electronic industries, this diffusion is coming into picture, where we see that integrated circuits all are fabricated using doping techniques. Okay, so the silicon material will be doped with other materials, and we want to have a controlled amount of impurities will be diffusing to the regions to change the properties. Okay, so these impurities have been diffused into specific regions of the device to alter the properties, that is like to improve the electrical conductivity. For example, doping silicon with phosphorus for n type of semiconductors. Okay, so we have, because in this they do all the diffusion is playing a role in establishing the properties desired on. Okay, so you can see that we deposit some layers on the surface and we have doping done on the surface. Okay. And if you want to look at how the diffusion is actually taking place in solids, if you take even two dissimilar metals, say for example copper and nickel are there. Okay, we take dissimilar metals like copper and nickel are made in they are made into some vulcanized and made in contact. What will happen with the time? So here the atoms the atoms of copper are there, atoms of nickel are there. Okay, so what will happen? So the what will happen is here it is high concentration, here it is very high pure copper, pure nickel. Obviously what will happen, this atom will try to move from higher concentration region to lower concentration region. So if you draw the concentration profile, so if you draw this is the center line at this location, from here to here the concentration of copper is 100%. From here to here the concentration of nickel is 100%. So that is, if it is 0 to 100, it is not varying here or varying here, it is totally 100 from this position to this position, from this position to this position. So what will happen if with respect to time, so the concentration diffusion of this copper alloy will take place from left to right, and diffusion of nickel alloy will take diffusion of nickel atoms will take place. So that's how this alloy of copper nickel alloy is formed. Okay, so in a copper nickel alloy we are going to have remember this is not only like when during formation it happens continuously, the movement of ions will be that. That's what we have seen, they are in continuous motion. One vacancy site is occupied by another material, this moves here, this moves here, let's keep on moving even when we are keeping it idle. Okay, so that's how
it is in the solid form only, sir.
yes, we are talking about diffusion in solids. Yes, in a crystal lattice within the structure. Okay, so the atoms keep moving from one place to another place. That's what we are going to discuss, how it will happen in solids. Okay, so what I wanted to show you here is with respect to time, once initially if they are separated, you have the 100% copper here, 100% nickel here, but after certain time, so their concentration will change, because from here to here diffusion takes place, from here to here diffusion takes place. We are assuming only one directional here, right? To understand the concept, we are assuming to be moving in one direction. Actually it happens in all three directions. Okay, so if there are several mechanisms proposed that how it is taking place, how the diffusion is taking place. Okay, so we can see there, this first case, one mechanism is interdiffusion. So interdiffusion refers to, in an alloy, atoms tend to migrate from regions of high concentration to regions of low concentration, as I explained. So I will show you here. Initially, the profile will be like this. What happens after certain time is, these atoms will move from left side to right, and some atoms from here will move to right. It's like you have a ordered class, all boys are sitting in left side, all girls are sitting in the right side. So after certain time during break time, so we don't sit in the same way. Some people move here to chit chat and we move our position, right? So that's what is interdiffusion. So assuming is that mutually there is exchange of seats. Somebody goes here, somebody comes here, right? This is interdiffusion. So the profile will be varying like this. And there is another diffusion is called within the same material. We here what we are talking about is bimetallic or alloy, bimetal alloy. Okay, so it's an alloy of two metals. We have this type of diffusion taking place. What happens in self diffusion is it's a pure element, pure atom. Then also there will be movement of ions. Say for example, in an element of solid, atoms also migrate from one place to another. Okay, so if you look at here, this is, if you tag the people, it is like tracking the movement of four students. Somebody sitting in the front row C, somebody sitting in fourth row A, somebody sitting in sixth row D, somebody sitting in eighth row B. So first lecture they are sitting here. After second lecture, are they sitting in the same place or not? If you try to track, what is happening is, so you can see that this fellow, somebody moves here, so this fellow has moved here. Okay, so this D from here has moved to this location. A has gone back to another row, and B has come one row ahead. Okay, so that way the diffusion of atoms will take place. Okay, because there is continuous migration of atoms. That is self diffusion. Okay, so that is, one is self diffusion, another one is interdiffusion. Interdiffusion takes place if you have two metals. Okay, you can, in simple I can say a species. Okay, in an alloy, if there are two metal species are there, one species will move to another species location, provided they are of equal size. Okay, so if you self diffusion is within the same atom, within the same metal, atoms keep on migrating. Okay, so if you look at the diffusion mechanisms, they are always, the atoms in any solid materials are in constant motion. They rapidly keep changing their positions. Okay, but for that, a person to move, what are the two conditions that must be available? One is there should be an empty adjacent site. Number two, there should be sufficient energy, right? We have to overcome the barrier, right? So I hope last week Valentine's Day came. Because of pandemic, we are not able to meet each other. But still, what happens? Somebody is there, single status is single. So you want to get committed. One thing is, somebody should be available a single for you to propose. Number two, you should overcome your shyness or whatever restrictions you have to speak, right? So you may be feeling things. So that way, there are two things required for atoms to move. One is there should be an availability of empty vacant site or adjacent, its nearby site should be vacant. Number two is it should overcome its barrier. The minimum activation energy is needed, right? So then only it can move. You see, for example, in class you are sitting in second row, front row is empty, and the faculty is going to come. You should have you should overcome your laziness to move from, get up and move to the front row, right? So that way, that these two are necessary for an atom to move. Okay, one is there should be an empty adjacent site available, and there should be sufficient energy to break the bonds with the earlier one. Yeah, it is like that bond is being broken, right? So from this row, because if you want to move from one row to another row, your friend may say, hey, don't go, you sit with me only, right? So that you have to break that bond, and then only you can able to move to front row, right? So that way, so this also important, that you should have an necessary energy to break the bond with the neighboring atom and then cause a lattice distortion during the displacement. Okay, and at any given temperature, it's not that every atom will be moving. only a small fraction of the atom is capable of motion by diffusion, and it is a function of temperature. If temperature is increasing, there will be more vibration and you will have more sufficient energy for the movement. Okay, and primarily there are two models which are used for defining this mechanism of diffusion in solids. One is called vacancy diffusion, another one is called interstitial diffusion. Either it can happen in terms of in self-diffusion as well as in interdiffusion. Interdiffusion is between two metals, self-diffusion within same metal. Okay, so we have two type of models are explained, proposed to explain what is happening, how the diffusion is taking place in interdiffusion and self-diffusion. So we have vacancy diffusion and interstitial diffusion. These are primarily, other three are also there. I'll let you know. First, to start with, there is a vacancy diffusion. So vacancy diffusion refers to there is an adjacent vacancy is there. Atoms exchange with vacancies. So applies to substitutional impurity atoms. It depends upon how, so the rate of this vacancy diffusion will depend upon how many, what is the number of vacancies available, how much activation energy is available to exchange. Means to move from here to there, that's what it's a like impurity. Here this impurity refers to another foreign material. Okay, it's pure A, it is B, so you have A and B, so there is a vacancy is there, so the movement will be like from here to here, it has to take place. So what will happen, there is a vacant site, what you will do, you will try to move here. Okay, so I will say, I'm thinking that this place is more comfortable to think. Okay, so what will happen next? So next, this is vacant. Then what will happen? Some other atom will try to come here. Okay, so this atom may come. It's not that only this atom will come. This for representation purpose. This either anyone around it can go here, or even this which has gone there can also come back. Okay, so like that with respect to time. So another atom will be moving from here. Okay, so that is this type of movement is vacancy diffusion, where you have clear vacancy so that you are shifting from here to here. Okay, so this is called vacancy diffusion, and it depends upon amount of vacancy. It's like vacancy is like empty site, right? So it's like how much vacancy sites are there in the lattice, so that one atom will try to move from another position to that position. So this will take place continuously, either even if you leave it at a room temperature, leave it alone idle also, that within the metal, whatever we are seeing the solid materials around us, within that this type of movement of atoms are taking place. Okay, it may be high at temperature. If it's a function of temperature, it may be at higher temperature, it may be taking place at faster rate. At low temperature, it may take place at slower rate. Okay, but this type of movement of atoms will be there. So another diffusion is called interstitial diffusion, where it happens when you have a system where you have two dissimilar materials, or one material having the diameter, atomic diameter, this atom is having of larger size, and another atom if you have it of small size. What happens, this cannot move from this from one gap to another gap. I think in introductory lecture also I told you that diffusion will take place like two big boys are there. I am lean person, I will be going through it. It's like several cars are there in a traffic. A bike fellow will, what will do, will he be in like queue line with behind a car? No, he'll find the gap between two cars, he will try to go here. Then you'll find another 2 minutes, he will 2 seconds, he will see another gap, he will try to go here, right? So that way the atom will, smaller atom will be moving from gap between two big atoms from one position to another position. It is called interstitial diffusion. Okay, so for this will happen with the case of smaller atoms like hydrogen, carbon, oxygen, nitrogen. So they can diffuse between some larger atoms in the solid materials, okay, metals. Okay, so this is before diffusion, after diffusion. They will keep moving from one position to another position. Okay, and in comparison to vacancy diffusion, this diffusion will be more, or you can say this is more rapid than the vacancy diffusion, because more mobile small atoms and more empty interstitial sites, because interstitial sites are more than vacancy sites, right? Obviously when you have atoms, instead of absence of atom, chance is less, whereas the interstitial, the gap between two atoms is always available. So this movement will be taking place faster in comparison to our previous case of vacancy diffusion, for which if there are more vacancy, more as we have already seen, if there are more vacancies, you are going to have more. But here, by default, you have more interstitial sites. Okay. And there is other three mechanisms also there. So interstitial C mechanism is, as the name indicates, it's combination of your two things. So if you look at interstitial C, so you can see that this atom between, because if they are loosely packed, you can see that this atom will push the actual position atom. This is an atom at the interstitial site. So here itself, if I try to tell, this orange atom is smaller in size. It won't have the energy to push this into other side. But if this also having equal similar size, if they have the energy, what it can do is it will push this major this into go into small gap. It's like in thing, some people coming and trying to, you have booked a seat, but that person is, even though lean, they will even push you to make you use it here, like that will move from our original position to side position. Okay, so that happens. So that is called interstitial C mechanism, where the interstitial atom will push the atom in the actual sites to go into another interstitial. So like that, so that will happen in thing. So once it is pushed, it will come here, but then this will go into this interstitial position. So that way also the diffusion can take place. Okay, so there is another concept called crowd ion mechanism. So actually here what happens is, one person, it's like one person want to bunk the class, if he leaves, he will take away 10 students along with him. So such type of mechanism is crowd ion mechanism, where an extra atom in a chain of close packed atoms can displace several atoms in the line from their equilibrium position, thus producing a diffusive flux. Okay, so that means one atom is moving, means along with it, it is moving, it has the ability to move at least 10. It's like one cycle. If this happens in case of closely packed atoms. If one bicycle is falling, it will able to, it won't fall alone. It will make neighbor cycles also to fall. Okay, so that way, in case of closely packed atoms, the movement of ions. So this movement, this is moving, means along with it, the others also moving, because of they are closely packed. Okay, such mechanism is crowd ion mechanism. So it's in the mechanism in where one extra atom in a chain of a closed pack atoms can displace several atoms in the line from their equilibrium position. Okay, so thus leading to diffusive flux. Okay, that is crowd ion mechanism. So we have another mechanism called diffusion along grain boundaries. This is what I was telling in case of metals. When you add chromium, what is happening in that one? Okay, so what happens here is, the diffusivity on a single crystal metal is always substantially smaller than that for a multi-crystalline sample, because the latter has diffusion along the grain boundaries and dislocations. Grain boundary diffusion is the most commonly observed route for solute migration in the polycrystalline materials, because there will be more defects at the grain boundaries. That's why it is generally accepted that diffusion in the crystalline solids proceeds more rapidly along the grain boundaries than diffusion through the lattice. And this may be due to atomic jump frequency in these planar defects, which is about 1,000,000 times greater than the jump frequency of regular lattice atoms in stoichiometric materials at 0.6 times the absolute melting temperature. So I repeat, due to the high concentration of defects in the grain contact area resulting from their crystallographic misalignment, this diffusive transfer along the grain boundaries occur much faster than in their bulk, where the defect concentration is much smaller, but slower than in the boundary between the solid and the atmosphere. Okay, because at the surface it is going to be surface diffusion, and grain boundary diffusion is one of the main mechanisms of low temperature sintering used in ceramic manufacturing and powder metallurgy. So increase in its contribution is usually thought to be the reason of a low sintering temperature, when finely dispersed raw materials are used. So grain boundary diffusion is also one of the deformation mechanisms in the solids. So for more details on this, refer to grain boundary diffusion, an historical perspective, written by Atkinson in the Journal of Chemical Society in 1990. In any metal or any alloy, when you have added some materials, what happens, even though you have distributed, see, if you add some materials into the metal to improve the properties, for example, corrosion inhibitor. Corrosion inhibitor is available in all forms, okay, solid, liquid and vapor form. So if you consider solid phase corrosion inhibitors, when these corrosion inhibitors are incorporated into the metal composition, so with time what they happen is, when they come in contact with oxygen, these corrosion inhibitors will align themselves along the grain boundaries and protect the material. Okay, so if it is a liquid or other, even in atmospheric vapor phase, they form a protective coating and protect the metal surface, so thereby combating the corrosion to take place. They increase the life of the metal. Okay, so this mechanism is diffusion along grain boundaries. Okay, so in the next lecture we will discuss about diffusion in porous solids. Actually it has its significance because we often come across, okay, or we have anything like even in adsorption will take place at the surface, right? So adsorption, so we are going to make use of a solid. Okay, this catalyst reactions, let me say. So in these solids, what we have, we will having some micropores, mesopores, we will have nanopores, depending upon the size of the pore. How the pore is there, I hope in CRE course you will be learning this. If it is a solid catalyst, so catalyst, it's not that it is only through outside the, if it is spherical shape, only outside surface, we don't have the reaction taking place at the surface. What happens is, we will have a big pore. Okay, so from that there will be a smaller pore. Okay, and from that smaller pore you will have even less smaller, means the diameter will keep decreasing. Okay, you can say that from that there will be a small pore. So from that you will, it's a model, mathematical model we can say. So you have, so same like a leaf. In a leaf, how you have bigger one going into smaller one going into further smaller one, like that we have, no? So similar to that, in any catalyst also, or even if you call catalyst, if it is used for reaction, or if it is adsorption, it is, you are going to have the same material. It can be carbon. Okay, it can be any catalyst also, platinum, everything. Okay, so you will be having micropores, mesopores or nanopores. That is from the, because if oxygen is there, if this is my reactant, let me say some C, what will happen, this oxygen will be diffusing through this, it will go through this small pore, it will be available, even the smallest pore, it has to reach there, and there it will get absorbed. What is the reaction taking place there? First this oxygen will get absorbed to the surface reaction will take place, then desorption will take place, then the product formed will be returning back through the pore to the bulk of the thing, right? So this is what we even consider for counter diffusion within the pores, right? So that's what we have discussed already also, but we will look into it in detail. Diffusion in porous solids. Okay, then this we will discuss in the next lecture. Diffusion in porous solids we will discuss in the next lecture. In this lecture, we have discussed about diffusion through polymers and diffusion through crystalline solids. Okay, so what are the different mechanisms that are taking place in crystalline solids have been explained. Thank you so much for joining my classroom. I hope you have understood the concept explained in this lecture. Please leave a comment. Thanks for your encouragement. Meet you in the next lecture. Bye bye.